So I'm talking here today because this is a duty asked of me for as we won the Innovation Award for international projects at last year's awards. So if you submit your project next year, just remember you'll have to do this yourself. The project is remarkable. I think it's a glass tube facade, and what I'm really going to talk about is the development of the system, how we came to the solution of it's a closed cavity glass tube, and Andreas from Seele is going to talk about the execution side of it, fabrication, installation, and development of the CCF system. So just zooming out, where are we? We're in Hong Kong. The project is in Kowloon, not on Hong Kong Island, in Kowloon, in a major kind of very dense urban area against the harbour. So Hong Kong, I guess a few things to say about that. It's a tropical environment, very hot, very, very humid, and really high wind loads, very high wind loads. The regulations there from an environmental perspective aren't very strong. Glazing U value that doesn't really feature. It's really just looking at solar control. It's a cooling dominated internal environment, and you have quite onerous requirements for occupied office areas, but ground floors, lobby areas, and that don't have high requirements for solar factor in that, which is why this is allowed to be very glassy. And so before you ask why is it 100% glass, that's why. Very low requirements. So the K11 project, K11 is a kind of shopping center brand. This is it's owned by a guy, Adrian Chang, and they also own Rosewood and hotels. So that is a 65-story Rosewood hotel off on the right-hand side of the picture. The overall development is shopping at the bottom, offices in the middle, residence on top of the kind of lump of the building there, and our museum piece is the bit in the middle, with the sort of Jeff Koons rabbit peeking through. The concept that we were handed when we got involved by the architect, who was so ill from New York, was what you can see on the left. It was eventually repeated on the right because the client liked it so much. It's a 9-meter high tubes of glass, and conceptually this was a kind of self-supporting glass tube that would span the height. It would be the envelope. It would provide a thermal function. It would be structural, and there would be nothing else. There would be no support. So this was our kind of starting point conceptually. So, given these kind of models and this aspiration, this kind of level of transparency, the kind of question was, well, how are we going to make these, right? Because if you cast your mind back to kind of glass technology at the time, 9 meters was a very big piece of glass. Sorry, I didn't say. This was started in 2014. So no one was really making 10-meter, 18-meter pieces of glass that you are now. When we were faced with this idea of the glass tubes, we kind of immediately thought, well, maybe think of SHOT. This is a kind of SHOT, if you don't know, they make borosilicate glass tubes for pharmaceutical, for industry, for lots of other applications. Not big glass facades typically, but it was where we immediately thought. We approached them. We actually got them to make us a sample. We got them very excited about the project. We talked, huge glass tubes. How are we going to make this? They said, well, we'll make the biggest glass tube that we can as a sample. So they went away and they made this. This was a sample for a 500 millimeter diameter tube. It's about 3 meters long was the longest they could do it. We got into conversations with them about could they make their machinery bigger? Could they, it's a vertically drawn glass tube, so they'd have to kind of dig out a basement underneath it to kind of do it. We actually got costs for them to do that. It's an ambitious client, and so we thought about that for a while, but then we came around to, well, maybe there's a more sensible way than this. So we thought, well, could you fuse? And they said, yeah, we could try fusing tubes together to make one longer one. It would all be monolithic, but you know, it was worth a go. So we came up with this idea, and they sent us. They said, well, "We'll do this, and we send you a sample." And the sample arrived in our office, and they said, "Well, there's a fused joint in the middle." We said, "Yeah, crikey, this is really amazing. It's really beautiful. There's like no imperfections at all. It was great." And then a few days later, another box arrived, also from a shop, and they said, "No, that's the sample. That was the full tube. The one that you've just arrived is the." And if you can't see it, like, there's a bit of distortion there. And actually, this is general. I couldn't get a bad enough photo of it. It's quite disturbing. So we kind of ruled that out, and we went back to another idea, which is something that we've explored in splice lamination, which is back in the old days again when you could only get flat glass at 6 meters and you had to make longer fins. You would lap them together like plywood, right? So we thought, well, let's just do these, and then we'll laminate some other tubes on the outside. We'll cut half tubes, and we'll splice laminate them around it, and that will also give us the benefit of it being laminated. So yeah, as I say, this is how, you know, we've been doing this for a long time with laminated glass fins, and that's, you know, going up to 15-meter fins and facades that we've done on, you know, many projects in the past. Same technology, and again, Shot did it. And so this was the result of it, because there were just the stresses that were building up in the glass. This borosilicate glass is very different thermal expansion coefficient to soda lime glass, and it was not moving and too rigid, and you know, in the autoclave it was breaking. So we had to abandon that. So we thought maybe we'll go back to half tubes and we'll go back to flat glass. Again, cast your mind back. This is what the precursor manual said at the time. This is the biggest that they could do. We knew that we'd seen some mock-ups that Krista Curva in Mexico had done for an experimental glass tube facade that didn't really happen. But we'd seen these in a magazine, and we sort of researched it. We contacted them. And, you know, eventually we started just to look around, and as we do, we looked all around the world, and we had, this was just half of the matrix that we put together from all the different glass people. You know, and this is from Mexico to Europe to China. And see Sam here, who did most of this research, I expect. You know, what's the maximum height they could do? What's the radius they could do? You know, in what thickness? What sort of laminate? What's the cost going to be? You know, and at this point, we don't know if it's how we're going to. Is it going to be tempered glass? Can anyone do tempered glass at this tight radius? Is it going to have to be chemically tempered, etc. Again, we contacted them. We got them to make some samples. Did a beauty parade of different mock-ups that they were able to do. And you know, a common thing was that just the quality was really, you know, not good enough because of this really tight radius. We ended up, sorry, there was some flexibility, but we ended up with 900 millimeter diameter, so 450 mil radius, outer radius of this glass. It was really tight, 9 meters long, and they really couldn't control it. After a lot of experimentation, Precursor got onto a way that they could fabricate this, and they did a successful full-scale mock-up, laminated, Sentry glass laminated, and this was the kind of point at which they'd mastered it, won the job, and that was the sort of chosen direction of the project. So. And then we've got to kind of really get into the design. So what we've decided is that slump soda lime glass is the answer. It has to be annealed. It's got to be laminated, obviously. And then if we're going to make full tubes, we're going to have to join them. We're going to have to figure out a detail to join the two halves of the tubes together. Thermal stress becomes an issue when it's annealed glass. Now maybe this routine, but nowadays, but this is the first time we've really gone into this level of detail and looking at thermal stress. We're in an urban environment, as I said. It's got a lot of adjacent buildings that are throwing shadows on this, and being annealed glass having very limited capacity for stress capacity. we need to know how much of the structural capacity is going to be taken up by thermal stress. So we carried out this, as you can see, casting shadows. How much of any glass tube is going to be in direct solar, solar going to be absorbing solar radiation? How much is going to be in shadows? We did this for for many points during the year, figure out what's the critical case, find the critical case, and we find the differential, the maximum delta T that we're going to have, and then we're able to take this analysis and add it to the stresses that we're getting from a structural analysis. Structural analysis. So as said, this is part of a big complex. There's a 275 meter tower right next to it. Here's the wind tunnel test. Again, I said the really high wind loads in Hong Kong. There's 8 kPa is the peak wind pressure suction on this tower, which is not uncommon. Luckily, and they also, well, I won't get into it, but the building department is also very conservative about many other aspects of it, such as the use of laminated glass. They won't accept composite action of sentry glass. They're more flexible now, but at the time they would not accept it. Luckily for our area, we've only got about 2.5 minus 3.5 for typical areas. We have these openings in some areas where there's a terrace on one side behind it, and we've got 5 kPa wind loads. So designing a glass tube to no composite action allowed between the joints, so we've got to design each of these individually for our modeling, and stresses are within limits on this 450 mil radius. We had these openings in there, which we were trying to create without any additional supporting structure. Initial ideas was that we would pick them up on a beam beneath that and span that onto tubes at either end. Modeled this. It worked if we were able to chemically temper the tubes at the end, but when we talked about that with Klima in time, but decided that wasn't a sensible thing to do. So we ended up with this structural model, where we've got a portal frame, which is framing out the opening for wind load, but the tubes that are on top that are above the portal frame are restrained at the bottom, but the portal frame is hung by rods that sit between the tubes up to a beam on top of the model, on top of the tubes, which then span across the opening and dead load onto the 2 tubes either side. And we've even got a case where it goes around a corner. So we're taking restraint from the building at the top, but all the load, the dead load of those tubes is being carried by a beam that wraps around a corner and dead loads onto beams onto the tubes at the end. Like this. So you can see here the rods which spend onto the beam and the beam bearing on the 2 end tubes. And final, we checked the U value, which wasn't very good. Now the final issue, but maybe this is a way to talk about it, that came up, and we're doing the design, which Andreas will talk about in much more detail, is the volume of air that you've got inside a tube is much bigger than what you've got in a flat in an IGU normally. And whereas if you've got pressure changes and temperature changes, where an IGU is going to pillow to accommodate that, a tube is rigid, fully rigid. There's nowhere for it to go. So this big volume of air that is going to try to expand and contract under barometric changes is just going to rip apart the seals. So we did lots of detailing on what we thought might be a way to solve that. We couldn't solve it. The only way you could do this is to have it pressure equalized, and if you pressure equalize it to the outside humid air, it's going to get full of humid air and you'll never be able to clean it, whatever. So we came on to this idea. Sorry, this is our final documentation. Here's our detail. Now, the The glass you'll see here is 2 times 12. So all of that analysis is only 2 times 12 glass with that curvature is able to do that 9 meter span. If this was a flat glass, this would be 7 or 8 plies laminated. So it's an extremely efficient structure. And I'll just point to the top. The way that we solved the pressure build up was to suggest that it be a CCF system, or somehow have some sort of pressure overflow into a bladder or something. And that was where we left it, and we said, over to you, contractor, to figure out how to solve this problem. Created a nice problem. We think we know what the solution is, but you're going to detail it. And I will hand to Andreas.
Yeah. Good evening. The only problem we faced at the beginning was we couldn't find that bladder. Yeah. So basically, so I structured my presentation a little bit prior to the event, but I realized I don't have to give you a talk about closed cavity technology. Yeah. So it's like being back in school for most of you. But Damian already mentioned why CCF was proposed. Basically, we had to deal with the large volume of air. The tube had more or less 5,700 liters of air. So if you think every 25 degrees of temperature, the air expands or contracts by roughly 10%. You're talking 570, 600 liters of more air or less air volume, which basically the tubes breathe in and out. And somehow we had to find a way to deal with it. Then obviously condensation in the cavity with the air exchange, which is somehow happening, is then also the topic we had to deal with. We had half tubes and full tubes on the project, 64 full tubes, and then there were 1 or 2 areas on the building where there was a concrete wall, and we basically could place only a half tube. So the half tube was closed with the flat glass at the back, and in order to make it a little bit more complicated, that had actually a reflective coating. Principal design of the CCF here, similar to the classic or traditional CCF system. You have your air supply and at the top, and then a vent at the bottom. And for our engineers, in order to get closer to the project, they obviously decided to do a series of tests to identify basically the ideal parameters to run such a system. Yeah? So first criteria was obviously to prevent any type of condensation in the cavity, but also one of the goals was to find the optimized operational airflow. So in order to do that, we did temperature studies. We also did studies on the humidity behavior in the tubes. We did climate analysis for Hong Kong, obviously, and we did tests with the airflow itself. Here you see a graph for temperature study for the half and the full tube. So it's straightforward, simple 2-day period, and you see are the temperature changes within the cavity over 48 hours. So what we realized here is that the half tube reacted actually much quicker to temperature or to solar heat gains and temperature changes in the environment. This can be explained basically with the fact that there is less air in the cavity, so it warms up quicker or cools down quicker, and also because of the reflective coating of the backplane of the glass. So in summary, you could say that the half tube is breathing quicker. The full tube obviously breathes a little bit slower, but with much more volume, because overall there is more air or the double amount of air in the full tube. Also worth to mention, we did those tests not only in Germany in our headquarters, we did them also in parallel in Hong Kong. The tests run, I think, even more than a year, and the engineers checked a lot, also the quantity of how does the temperature in the cavity change. So do we have really quick changes or slow changes? This is shown here in that graph. So we have a scale which shows basically the temperature sections where the temperature changes over a period of 1 hour. So, and as expected, what you can see here is that you have a more stable temperature in Hong Kong, whilst in Germany or Central Europe, you have, because of the bigger differences between day and night, you have larger temperature drops over 1 hour. We did a similar test for the partial vapor pressure. This is basically to check on the humidity. And as Damian already mentioned, humidity is much, much higher in Hong Kong than here in Europe. So what happens is that even we don't have such a large temperature drop in Hong Kong, we still get, because of the high volume of humidity in the air, much more humidity into the tubes than we would get in European conditions. So in order to control the humidity in the tubes, we did tests with different airflows. So just to remember, we have 5,700 liters of air in the tube. So we had to find out, okay, how much air do we have to pump into the system? So we basically started at the top with, here in this graph, it shows 720 liters per hour, then lowered it to 150 and went down to 20 liters per hour. And what we checked during that test was basically the temperature difference between the temperature in the cavity and the dew point. So you can say the higher the temperature is, or the further away the temperature in the cavity is from the dew point, the less risk you have of condensation. So what you can see, with only 20 liters per hour, you have actually lots of instances where the temperature difference is 0, and we experienced condensation in the cavity in those instances, or up to 5. So obviously that airflow was far too little to accommodate a functioning system in the cavity. The graph here from the experiments or from the tests shows that a flow of 150 liters per hour would be sufficient. I think ultimately we applied the airflow of roughly 250 liters per hour also to give some residual safety to this overall system for the facade. A few design details. So this is the full tube. What you can see here, the 900 millimeter diameter, and it's probably better to show here. This is our connection detail for the full tube. So similar to what Eckersley O'Callaghan had designed initially, we have an aluminium profile which is structurally bonded to the edge of the glass in between a gasket to seal the system, but also to accommodate the tolerances. And we have an additional carrier profile on the outside for LED lights, which run in the vertical direction between the tubes. The key of that detail is basically to accommodate all the fabrication and installation tolerances. That's why, and obviously also the structural requirements of the system itself. Also not part of the CCF, but worth to mention, the half tubes. There we glued the carrier profile or the aluminium profile on the surface of the glass. And then similar to the full tubes, also providing a support for the LEDs. At the bottom and at the top of the tubes, we installed stainless steel caps just to provide an enclosure and also a structurally sound finish. They are all also structurally bonded to the glass. And then the whole system is actually supported on a single stainless steel rail, which is fixed to an embedded plate on the ground. This is the detail for the half tube, so that's why the support is further at the back. For the full tubes, the rail sits almost in the center. At the top, very similar, also a steel cover. I'll show you later some pictures, which is structurally bonded to the tube and then with some stainless steel bracketry restrained to the back of the building, to a hyphen channel. So these are some photographs from the factory from Eckersley, which Damian facilitated. So the key for the fabrication of the glass was obviously to provide that to us within the required tolerances so that we could do the assembly. This is how the two glass pieces go into the autoclave. And then we decided to assemble all these tubes in Hong Kong. So basically all the elements were delivered to Hong Kong, and that helped us basically to avoid the hassle to transport those finished tubes over a long distance across the world. Because as soon as you have the tube finished, you have always to maintain the airflow into the cavity because of the constant pressures which are happening even during transport. So we actually set up a clean room in the, you can almost say, most expensive area in the world, in a warehouse where our team assembled all these. So, and you need to have a good level of, or good skill of workmanship to make all that happen. And sometimes it's very helpful that you have people which go back to very basic means and methods. Yeah. So this is just the check for the tolerances of the glass, a simple steel template, which you put over and you see whether it's all right or not. Here's some images from our warehouse. So overall, we had 309 tubes, I think, yeah. Half tubes and full tubes. So this was also a logistical effort. This is the clean room where the assembly of the tubes happened. Because of the geometry, we had to make sure that our people had good access to carry out all the silicon work. So we basically teamed up with a supplier in Germany who provided us with this special rack where we could place all these tubes and turn them 360 degrees so that we could access all the areas from all angles. So you can see also in the body language here that it's still in development. Yeah. So, and this is how it comes then all together. So the tube or the glass on the rack, and then our prefabricated stainless steel caps also supported, and we could slide them carefully on and then carry out all the quite extensive silicon works in a safe manner. Yeah, and then we came to installation. So the first element which was installed was all the stainless steel piping for the CCF system so that the tubes could immediately connect it once they were installed on site. Here just the apparatus for the airflow, for the air supply. And here are some images from site now. all the scaffolding in Hong Kong is bamboo. The blue line there you see, this is our support rail where the tube sits. So that element was actually key when we did the setting out in the first step of the installation. Once that rail was set, the final position of the facade was already determined in a very early stage. On the right hand side you see the start of the support bracketry for the top. And because the building is actually quite close to the water, so you get quite some dramatic images from the installation with tubes flying across the sea. So lots of tower cranes were involved. We had to develop also a special glass sucker similar to precursor to manipulate the elements on site. And at the end, I show you some finished or images of the finished project. And I think they come 100% close to what the rendering said at the beginning. So this is a small movie about the LEDs here I had. 1 second.
It's got to be light show.
Yeah. Yeah, I think that's the image of the rendering.
Yeah.
You showed.
Yeah.
Yeah, Eckersley or Callaghan, I think, or Cruiser, I'm not sure who it was, made then a little aftermath.
Well, the project, yeah, as I said, we started the project in 2014, and then there was a bit of delay along the way, and everyone, Cursor had made the glass, and we were all excited about it and wanted to, didn't want to wait for the project to be finished. So came up with the idea of, Lisa came up with the idea of building a slide for GlassTech 2016, I think it was. And yeah, so that was it. So this was the 9-meter piece of glass is the slide, and I'm not sure what the is, 4 or 5 for the ladder side of it. And it was just a bit of fun, sort of showing what could be done in the transparency. So, and what we also did here was that we did use the shot. These are shot solid tubes for the rungs of the ladder, and those were bonded with TSSA to the side. So whatever it's called, transparent structural silicon adhesive from Dow, the clear, super strong adhesive, and yeah, and that was just a kind of fun and beautiful thing to do with it. I think that's it.
Very good.
Questions for Andres?
Did you go down the slide?
No, I didn't. I didn't see that. I was in London working when people were sliding. Yeah.
There's quite a lot of friction. I think there needs to be a special
plastic or something.
Yeah,
Trousers.
yeah, special trousers. Or,
Brown ones.
yeah, if you were polyester, it just went up in flames. Yeah.
Presumably it's low iron glass.
Yes, it is.
And where was it sourced? The plate?
I'll struggle to remember that. It might have been. I mean, around that, I'm thinking of other things we were doing at that time. Were Pilkington in the Nuremberg. I think they had their sort of super low iron glass. It might have been that.
Super low iron.
But for like solar, I'm not sure if it was super low iron, but they did. They were, and for some projects we were getting their, like for solar farms, they do a very low iron glass, not really for architecture.
Did you make any spares in case there are any replacements required?
I hope so. Given precursors.
We left all the installation equipment in Hong Kong because if you have a damage, you have to replace the entire tube. So you take one out and put another one in.
Did the system have to accommodate much lateral movement?
From the building.
Yeah.
Not much, no, because despite the high loads, they build correspondingly thick columns and walls. There's a lot, there was quite a lot of concrete in the superstructure. So no, it wasn't significant. You can see there's a rocker, but in plane,
Yeah.
there's not they cantilever, I believe.
Right.
So there's not a lot of need for that. But it does get critical around the portal, because that portal you see is, well, if the tubes try to rack over that, then you do get a lot of movement. So no, it cantilevered from the base and just rocked out of plane.
Okay.
Bruce?
Did you use any coatings at all, or considering?
We tried, but that was there was a lot of experimentation with coatings, and on the curved, and it was really difficult. So yeah, most of it failed, and as in the visual quality was no good, or the coatings burned, and in the bending. We did have some success. I'm not sure I'm allowed to say, but who was successful. But it did work, but it was visually in the end. Chose not to.
No coatings?
No coatings. No, but this OTTV is the solar way they deal with combined U value and solar performance of the facade, and it adds up the solar transmission of the glass and the U value of the opaque wall. So U value of glazed walls just doesn't factor at all. And if you're in a lobby, it's effectively, you can use clear glass. And above that, you need a solar control coating. So a lot of the wall, you might have seen it from the images, it's actually not occupied space directly behind it. There's a lot of opaque walls, which is why we've got so many of the half tubes. So most of it, even of probably 2/3 of it, has a wall behind it.
So you were lifting with a glass sucker, so you had all the profiles bonded to the edges of the glass. So you weren't able to use them to lift in the profiles?
Good question. I don't know. I think glass maybe as a secondary restraint or so, but the glass itself was taken. The tube was taken with the glass sucker. Yeah.
I mean, the profiles are
very
super
thin,
minimal.
yeah.
They're not doing anything structural.
Look big on the screen.
Yeah, but the tube would go almost out of the window then, yeah.
I noticed on the half tube, you had a large deflection at the edge of the half tube. Was that due to the pressure, or was that just due to expansion?
That is just the deflected shape of the tube when it's constrained at the top and the bottom.
Yeah.
In the shoes, so they're all rigidly connected, but in the middle there's nothing spreading keeping the glass from spreading out. So we had to talk in the pub about this, but the composite action basically is not allowed, right? And so you have to design each of those. We just had to design each half tube as two 12mm monolithic pieces, we're taking half the load. So it's 50% load share between the two pieces. You can. Anyway, so and
that's
the
wind load deflection.
that was just a wind load deflection of it flattening out in the middle. It's not exactly because it's constrained on the two sides. It's also got another
It's also two lamps
but
together.
bonded to each other.
Yeah.
No, but that's it.
The composite action, you were allowed to take in each of the laminates from the halves, but you couldn't take them from the front to the back.
You can't take them in the laminate.
Yeah.
And we didn't, because there were cases, we didn't talk about it. There are some cases where it's just a half tube without a back to it as well. So that was the critical case. So we didn't look at that. Yeah. Yes.
What sort of performance testing did you do, and where did you do it, and to what standards?
Hong Kong standards, obviously, and performance test was done in Germany, and we've done one typhoon during the installation as well. So that was, I didn't bring those images unfortunately, but there was a typhoon during installation, and there was actually lots of glass damage in Hong Kong. It was even in the news at the time, and you could see damaged scaffold and scaffold protection everywhere, but the tubes did withstand that load test.
Given Chris Cursor's slumping technology and Seele's autoclave technology, can you make them longer than 9 meters? Having got this
bet
far,
you could
could you
now.
do it?
Now we can, yeah.
If an architect came to you and said, what, 12
Yeah.
meters?
Yes,
Yeah,
18, I think.
well, that's the biggest bit of, well, I didn't get 20 up now.
Don't encourage them, Chris.
Well, no, I was going to say there are no architects present, so I think it doesn't matter.
Oh, I was talking to architects last week, and they had actually a nice project with more than 2,000 tubes, but they were all very small in diameter. So goes back to short.
Right.
Thank you very much.
Thank you.
Thank you.
Yeah, thank you.